So, a very good afternoon, ladies and gentlemen. I'm Dr. Tay Ziong from the Singapore Institute of Technology, and I will be the moderator for the technical session today. On behalf of the Singapore Society of Floating Solutions, I want to welcome everyone to the this second technical webinar organized by the Society. So, before we begin our webinar, I would like to remind everyone to mute your microphone at all time. All questions to the speakers should be posted in the chat group, and the speaker will be addressing the questions and comments on the talk at the end of the talk. So please do note that this webinar will be recorded and the video will be shared in the public domain. So today we are honored to have Dr. Victor Nian, a senior research fellow from the Energy Studies Institute, NUS, to give us a talk on the perspective of a marinized offshore charging station for electrifications of the maritime industry. So Dr. Victor Nian has a wide range of experiences in the energy studies. Besides holding a position as a senior research fellow in NUS, he is also a visiting fellow at the Hughes Hall, University of Cambridge, and an adjunct professor at Tianjin University of Commerce. His expertise is in energy and nuclear policy, energy systems analysis, technology assessment, and digital system integration. His research portfolio includes a diverse range of interdisciplinary projects supported by the government, departments, and industries. So this talk by Dr. Victor Nian is to attempt a critical questions on the economics of offshore marinized charging stations for enabling long-distance freight for fully electric vessels. So without much further ado, I would like to invite Dr. Victor Nian to take over this webinar. Dr. Victor Nian, please.
Thank you, Dr. Tay, for the nice introduction. It's really a pleasure to speak to in this webinar for the Singapore Society of Floating Solutions Singapore. So maritime research has always been maritime industry has always been an interest in the energy field. And very often, we tend to say that it's very difficult to decarbonize, there's very limited options, and yet it is a very important industry that carries our economic development. So just a couple of years ago, or rather last year, we started a collaboration kind of a preliminary studies with Shanghai Maritime University. He's actually one of our ex-colleagues from ESI. We wanted to just look at whether it is possible to actually electrify the international shipping industry and how that might contribute to decarbonization in the future. So this study, or rather this webinar, will give you some of the results that we have derived in our preliminary assessment. So before I go into the webinar topic itself, I would like to give a brief introduction of the Energy Studies Institute. So Energy Studies Institute, in short, ESI, is an autonomous research institute that is established at the National University of Singapore. So we were founded initially by Ministry of Foreign Affairs in 2007, as at the time energy security, energy impulse was deemed to be very important issues for Singapore. Later on, the Ministry of Trade and Industry took a very strong interest in the institute's activities, primarily because energy really is the backbone of economic development in most countries, and Singapore is no exception. And then, of course, the Ministry of Environment and Water Resources, now it's called Ministry of Sustainability and Environment, joined the so-called stakeholders, and these three ministries now become the three main stakeholders for ESI. And we work very closely with the government as a policy think tank, but we're also keeping arm's length from the government so that we can deliver independent assessment and analysis of energy issues. In addition of the three main ministries, we also work with the agencies and statutory boards and the respective ministries for specific project topics. And maritime research is one of the important topics in our research portfolio. So in the past, we have been very much looking at individual divisions, but moving forward, we are thinking of setting up multidisciplinary research areas or research programs, if you like. So one of the key areas is what we call the smart urban energy economy. So this is driven by the agenda of digitalization, of digital transformation of the energy sector or energy systems. So when the energy system becomes smarter with smart meters, smart grid energy management systems, autonomous vehicles and electrification. So how can the entire energy economy in the urban context become smarter and more resilient? And then as a policy think tank, we remain very interested and strongly grounded on energy, climate, and industrial policy research. So we bring together different expertise from economics, social science, engineering, technology, geopolitics, politics, and political science, we work together synergistically and looking at these policy issues from a multidisciplinary approach. Hydrogen now is becoming a very big topic worldwide. And with this reinvigoration of hydrogen economy becoming a really important topic today, and also Singapore spending a lot of efforts, devoting a lot of efforts and spending research grants on hydrogen economy, we feel that this is an area that deserves much stronger attention than before. So we are also looking at setting up a hydrogen economy research program in a multidisciplinary setting. Another important topic is, of course, energy transition. Everywhere we're talking about how do we move from a fossil-dominant energy economy to something that is more sustainable, maybe more renewable energy with battery storage, maybe even nuclear energy, hydro, LNG, and CCUS, carbon capture, utilization, and storage. So those are the things we're talking about in terms of energy transition. But of course, when COVID-19 hit us in early 2020, that made us thinking, what else needs to be done and what should be done, should we have done, in accelerating energy transition in the post-COVID-19 world. That probably entails greater collaboration in the region, in the ASEAN context, maybe better trade arrangement, and maybe stronger attention in R&D, in new technologies. And so bring together, in order to answer these policy questions or strategic questions, we need the necessary tools or the right tools to answer those questions. And of course, energy modeling has been our close friend when we address policy issues. But very often we realize that tools and the computer simulation models are very often working in silos. So you have the engineering model, the computational fluid dynamics. You have hardcore econometric model looking at the economics. And you have some environmental impact assessment model. You may do some life cycle analysis or techno-economic assessment. So what we're thinking is there needs to be a synergy among all these tools, perhaps a platform or perhaps an alternative tool that will be able to unite all of these modeling efforts so that moving forward into the future, we are able to address the questions or the strategic concerns from climate change, from resilience, using this platform. And precisely because of that, a group of us from different parts of the world, so in this case, we have experts from Sweden, Australia, Germany, Japan, China, different countries. We came together and said that, well, research and academic research, technology innovations, really these are things that should be shared across the world in order for us really to benefit in terms of innovation. So the editor-in-chief of Applied Energy, Professor Nian from KDH, he came up with an initiative, says, well, why don't the like-minded individuals and researchers come together and form what we call a unit lab. It's like a research grouping that we're all interested in. For example, in this case, we're all interested in integrated systems analysis. We come together, we share our knowledge, we share our research experience, we even share our papers and organize workshops and conferences, all on the same theme. But of course, some of us may be working on methodology. Some of us may be working on the economic theories. Some of us may be really looking at consulting works and addressing real life issues. Some of us may be really in the engineering field. But we're all interested in this so-called integrated assessment. So we come together, we form this research network, and we publicize the research grouping and also our research findings. And very often we organize workshops. In fact, the topic today came from a discussion, or rather a workshop that we organized with the Asian Development Bank Institute just earlier in 2020. So of course, moving into the future, in the past, of course, we look at climate change, but we shouldn't forget about there's a greater extent of sustainable development. Very often in the world, or in different parts of the world, besides Singapore, it's not just about having mitigating climate change, improving energy efficiency. There is also the issue about energy access. There is the issue about modernizing energy systems. There is the issue about how to develop industrial capabilities, economic development. So all of that actually forms the greater boundary of our studies these days. And actually, in a way, you can say that maritime electrification might actually help improve or contribute to these sustainable development goals. I will explain later in this webinar. So now we're going into the topic. So of course, when we talk about international shipping, I mean, if this word issue international shipping being mentioned, I think the first thing that comes to most of our mind is carbon emissions, pollutions. This is really the most prominent issues that's been discussed everywhere. The Intergovernmental Panel on Climate Change, at the UNFCCC discussions, at the IEA level, even in the regional level, we talk about decarbonizing the maritime transport. And truly enough, if you look at the historical data from the International Energy Agency, the carbon emissions for maritime, for shipping industry has been quite stable. You might say, well, actually, we're not doing that bad. If compared to what is happening on land, the carbon emission is fast rising, right? With urbanization, industrialization, carbon emissions are, is really on the rise. Whereas in the shipping industry, we're not doing too bad. We're quite stable. But then, of course, there are other issues with this stability. Is it because we don't really have that much options to decarbonize, or is it because of other issues? Right? So then moving beyond the decarbonization of emissions, if you do look at the reality of the global economic development today, if you look at United Nations, they were saying maritime transport really is the backbone of global trade and the global economy. So no matter how dirty, how clean, or how sustainable it is, for shipping, it is very important to us. And then the International Energy Agency further echoed, actually 3/4 of the total freight transport activities are on the backs of international shipping. And although it contributes to lots of carbon emissions globally, it still is the most energy efficient way. Of course, this is the IEA's view, right? It is the most energy efficient way to carry cargo in terms of energy use per ton kilometer. Excuse me. But then, of course, if you think about transporting crude oil or containers in bulk, you wouldn't think of doing that over airplane or on land where there's no physical connections. But of course, the IMO, or International Maritime Organization, is stepping up its effort, and it wants to cut the absolute greenhouse gas, that's GHG, greenhouse gas emissions by 50% by 2050. And it's also looking at legally binding measures to reduce carbon intensity of international shipping by at least 40% by 2030. And they're also trying to reduce the intensity by 70% by 2050 compared to a physical 2008 baseline, rather than using a simulated or projected BAU. This is actually 2000. They want to benchmark against a real number. So, just to look a bit closer, looking at the current effort by the International Maritime Organization. Right now, they're looking at energy efficiency design index for new build. These are for new ships, and for ship operation, there is an indicator called the Ship Energy Efficiency Management Plan, where you can evaluate how efficient or the carbon intensity of shipping or transporting cargo. And then, of course, for existing ship, there is the energy efficiency existing ship index. So if you do a retrofit for a ship, then there are these indices for you to benchmark against a set of standard or indicators. There is also the carbon intensity indicator, which was also applied to existing ship. So these are all providing some guidance on how the shipping sector can become more energy efficient or become less carbon intensive in the future. And then, just to help the shipping companies or the shipping industry as a whole, back in 2011, there were already more than 50 mitigation measures that has been proposed by the International Maritime Organization. So these measures include quite a number of different directions. I mean, there are technical measures, for example, modifying engine, different coating, draft designs, and route optimizations. Draft designs. And then there are operational measures such as optimizing the route, better forecast of better conditions, and also maybe optimizing fleet operations. And then, of course, among all of these measures, you will read that there is an emphasis. It says that no matter how much you can do, if you really want to go for deep decarbonization or make the maritime transport really clean, you have to do something with the marine fuels. So right now, we're still dependent on the bunker fuel, and IFO 380, or right now it's probably going to 180. The argument is no matter how energy efficient or how clean these fuels are, they are still very dirty bunker fuels, and they produce huge amount of emissions en route. So the topic on sustainable marine fuels came about with a question, actually. So what are the options that's being talked about and being discussed? Then, of course, in the news, you hear about using LNG, liquefied natural gas, as a potential fuel to kind of diversify from the current IFOs. I mean, LNG, from a pollution or carbon intensity point of view, of course, it has become much less carbon intensive and it's much cleaner in terms of pollution as compared to IFOs. And then, of course, there is the discussion about ammonia, maybe even hydrogen. But there is the question about how efficient it is to actually burn ammonia and hydrogen, and also the energy intensity of these fuels. I mean, for long-haul international shipping, the energy intensity is actually quite important if you want to achieve the kind of distance, which also impact the refueling or stockpiling strategies for shipping companies. Then, along the agenda of electrification, just like what is happening right now on land, we're looking at electric vehicles. There are, countries around the world, including Singapore, we're actually looking at fully electrifying the land transport with EVs, electric trucks, electric buses. The electric buses are already running in the Singapore fleet. So we asked the question, can we actually use full electric ships in the long haul for long haul shipment in the future? So as I mentioned briefly earlier, a collaboration between Shanghai Maritime University and the ESI, we started off with a kind of fundamental research, right? We want to look at life cycle analysis of international shipping, and then we want to do a techno-economic assessment of the different ships, and also looking at transition pathways towards more sustainable shipping options. So this is really fundamental research, looking at modeling what are the methodologies that is relevant in the context of maritime industry. Then we came up with the idea. So this is 2019, actually, 2018, 2019. We were thinking, can we actually electrify ships? But then we quickly realized there are a lot of other issues, which I will explain. So then we say, well, okay, let's look at electrification and see where the potential bottlenecks are and how economically competitive that electrification is in the maritime industry context. So we did a little bit of literature review by looking around the world. Actually, there are companies that are already designing and developing relatively large scale. I mean, there are not this E5 ship is not big, and it's not as big as you might think, but it is big enough as a like if you like demonstration vessel. So it's fully electrified. It's called E5 on the Japanese website. It's because it represents electrification, environment, economy, efficiency, and evolution. And the E5 consortium was actually established by 4 companies: Asahi, Exxon, Mitsubishi Corporation. These are the so-called leaders in setting the consortium. And later on, Inamitsu, Tokyo Marine, and TEPCO joined the consortium to really develop this vessel. So from the E5 ship website, you can actually find more information about the vessel. It is still under construction as of the last time we, to our best knowledge. But these are the so-called specifications that the company is looking at. There might be minor modifications eventually, but these are the information that's been published as of today. So it's not a very big ship. It's only 500 tons. At a speed, you'll be able to operate at a speed about 10 knots. Cargo capacity is about 15,000 tons. And it's fully electric with a onboard battery of about 3.5 megawatt hour of battery storage. So we calculate the distance. It's not going to give you, a very, for full charge, it's not going to run for a very long distance. We were looking at, if you really run the ship, without charging, you run from A to B, it is probably just within some of the ports in Japan itself. And even in the context of Southeast Asia, it is probably very difficult to even go from one major port to another on a full charge. So by looking at what is the state of development, we were thinking perhaps with one-step charging, a few charging stations, this may help extend the range for sure, but we do not know how that might affect the economics of shipping, when you have charging. And there are not many charging options in the world today. So the reason, just to backtrack a bit, before we talk about charging, we look at the issues with the land-based vehicles. So the good part is, you don't have any tailpipe emissions. Electricity is generally cheaper as compared to fossil fuels, and especially in Singapore's context, where there's a high tax on fossil fuel, on petrol, on diesel. So electricity seems to be a little bit cheaper. It is also convenient to refuel at home. You can actually charge at home, but this is with a caveat in Singapore's context, because if you want to have a charger, if you're living in an HDB apartment and you want to have charging, that is a different story. But if you do have landed property or private properties, charging is a possible option. And of course, companies will claim this lower maintenance. You don't have to do like oil filter replacement and the other maintenance you would normally see on the internal combustion engine, because now these are DC motors, and very likely they are brushless DC motors, so the maintenance costs can be much lower, and they're quieter and much less noisy as compared to internal combustion engine vehicles. So the problem is, these are very obvious problems. The range is very limited. If you fill up a petrol car, full tank, you can cover much longer mileage as compared to a fully charged electric cars. Then of course, Tesla may come on and say, well, with our state-of-the-art battery technology, we can actually cover almost the equal distance as your petrol car. But then if you think in the context of maritime vessels, this is probably not going to be the case, at least for now. And then on land, we already have this problem of access to convenient fast charging infrastructure, and I must emphasize the word fast. Fast charging infrastructure is not always easy and convenient, and fast charging also induces a lot of stress. Maybe not to the main grid if you think in terms of Singapore's context. We are relatively small, and our grid technology is relatively advanced. But it does place a lot of pressure on the region, on the substations. If you think about Ang Mo Kio district, or if you think of Queenstown district, and if you have a lot of fast chargers for cars in those districts, then when all the cars are plugged in, you will induce tremendous stress at the substation transformer level. But to the main grid, perhaps it doesn't really cause that much disturbance. And of course, for now, mostly because of the cost of battery, electric cars are still very expensive, especially in Singapore's context. If you look at the Tesla Model 3, it's actually way much more expensive than Toyota Prius. And one other thing which is probably less relevant is that if you look at the petrol cars, you have a whole range of choice. Even within one company or one brand, you can have different models. Whereas when it comes to electric, you do not really have the luxury of choosing the different kind of models or sizes. And the most important thing is, if you want to have fully electrified road transport, then then you are basically moving issues from the so-called mobile combustion pollution to stationary pollution. Why we say that is because the power generation or the power sector today is still dominated by fossil fuel. In Singapore's context, we are 97%, maybe more, on natural gas. And looking around the region, Malaysia, Indonesia, Thailand, these are the countries that are heavily dependent on coal. So a large-scale electrification may or may not make sense from if you look at the life cycle environmental impact. So the same thing would apply to the maritime industry. If you electrify ships, right, and then you go to the port and charge, and that port is primarily dependent on coal-fired power generation, then it is probably not doing anybody any good as a whole system. But if you go back to the range problem, if you go back to the battery problem, we have to admit that no matter how clean or how convenient or inconvenient it is, charging is going to be a necessity for long-haul freighters. If you want to electrify let's say a long-distance oil tanker, for example, let's say you want to ship from Singapore to Qatar and back, you will definitely need charging. There's no way you can ship from Singapore to Qatar on a full charge. So here comes a very practical problem. Weight and volume are the major constraints. Weight not so much, but volume definitely is a constraint for ships. and energy density of the present lithium-ion battery fully charged is nowhere comparable to the bunker fuel that you will carry on the same volume basis. So, and also battery safety, thermal management, life degradation, these are all very practical issues, and it really is a bottleneck for the moment. So, yeah, as I mentioned, is if you really want to fully electrify vessels with batteries, is that even possible today, just to do it? But of course, in our study, we just assume that, okay, since E5 is going fully electrified, so there is the possibility that you can fully electrify a ship. How economically viable, how technically feasible, or whether it is even a viable option from this whole economy of charging and moving cargo is concerned, these are the questions that we need to ask. So that brings us the inspiration of looking at offshore marinized charging station. But before going for charging, the power has to come from somewhere. So fortunately, we don't have to make very much wild assumptions on floating, offshore power generation options. So, I mean, in the early, not so early days, offshore wind has already been largely developed. And there are quite a number of very notable large-scale offshore wind projects in North England and also in the Scandinavian region. So offshore wind is no alien to us. We're very familiar. Solar PV in recent years has received a lot of attention. Cost is going down by a lot, and the efficiency has been improving gradually. So along the lines of offshore wind, we will naturally assume that offshore or floating PV is possible. I mean, it's demonstrated possible. You can do it on reservoir, you can do it on near shore, but perhaps with technology innovation, with new engineering method, it is also possible to scale up offshore wind, offshore PV as a power generation option. And then, of course, offshore floating nuclear power plant today is no imagination either. Rosatom just recently completed the construction of the KLT-40S, or it is also known as academic Lomonosov. So the larger image on top is the barge in which the twin nuclear reactor is installed. It is a barge, it's not a fully operating boat. So, but now the ship is now already operating in the northern part of Russia, providing electricity and heat to the neighborhood community. So this is a demonstration project, but still we managed to find some cost numbers and also read capacity of the power plant. So we're hoping that through some assumptions, we'll be able to do some preliminary analysis on the floating nuclear power plant. In the beginning of our analysis, back in 2018, 2019, we were thinking, how do we find some valid assumptions on charging? What kind of charging are we talking about? On land, you can say, well, I have a charging station. You can park the car in the car park, and the chargers are installed. There's no problem with that. If a thunderstorm or anything, at least you can have some simple shelter to shelter the charger, and with some weatherproofing, right? And you can actually plug in your cars at the charger. It's not a problem. Whereas in the open sea, what can you do? Is there even anybody thinking about installing charger out there on the open sea? So at that time we're thinking, well, let's just assume that somehow engineering companies will be able to make this possible. Weatherproofing chargers shouldn't really be a problem. You can weatherproof, you can waterproof or weatherproof nuclear power plant. You should be able to weatherproof a charging station. So true enough, to our a little bit of surprise, this is actually a bit further research. Actually, back in 2016, the company, I don't want to pronounce the name wrong, Data and Cavtech, they actually were developing this concept of wireless charging. So it's like induction charging for the mobile phone, or the induction charging for electric vehicles that's being explored these days. So what you do is you place this induction coil on the side of a vessel, and then you can actually charge the vessel without having to have a physical plug in it. And then 28th of September 2020, Maersk also come up with a proposal to do a floating buoy where you can It's like a charger, but you can connect this board to a ship. Let me just show in the picture. This is just a conceptual picture. I don't think there is a demonstration prototype yet, but I stand corrected if that is not the most updated information, right? So the idea is to leverage on the offshore power station to power the charging buoy, and then charge the ships as it comes close by. But then now we're getting some comfort that says that in saying that offshore charger is possible. There are companies that are willing to devote their attention, even willing to do to implement the physical demonstration project on it. So what else is needed? What else is missing? So we then, go ahead with a very rough, you might say, simplified assumption. So let's just assume that it is possible to simply integrate one of the offshore charging power generation technologies with a charger, and we think, or rather we would imagine, that you might need some kind of battery energy storage to be packaged in this whole scheme of charging, because there are bound to be ships in a hurry, and you want to boost up your charging power so that very quickly you can fully charge the vessel. Or maybe at times when the wind condition is really good or the solar radiation condition is good, there is so much electricity, and you don't want to waste those electricity because those are actually valued when later on I explain how that comes into the economic calculation formula. You want to store those excess energy in some form of energy storage. So in this case, we just assume, well, lithium iron phosphate battery is one of the most, I wouldn't say most economical, but it's the most popular energy storage technology being discussed when it comes to grid connected battery energy technologies. So then we said that, okay, there are three options: offshore PV, offshore wind, and offshore floating nuclear power plant. There is an onboard battery storage. There is this fast charging. And we also made a very bold estimation of 15 minutes, you fully charge a vessel. And 15 minutes is only based on the assumption of E5 ship, right? It's about 3.5 megawatt hour storage. So the assumption is ship comes by fully empty, it won't be fully empty, but fully empty, 15 minutes, fully charged, go to the final destination. So this is a very simple assumption on the route. And here are much, much more assumptions, okay? So this, I must remind everybody that this is still a preliminary analysis. The assumptions are only to our best knowledge, and we took references from quite a number of places. So if you feel that the assumptions are not justified, you think that the assumptions should be adjusted, or if you have data that you'd like us to collaborate with you, we are very happy to hear your views and comments on these assumptions. So right now, just allow me to go through these assumptions very quickly. So we did talk to some shipbuilding companies on the cost. The general consensus is yes, you have batteries for E5, but the overall investment cost for a ship will be in the order of magnitude that makes your small little 3.5 megawatt battery cost becoming really, really small. So they say that maybe we can assume a $0.7 million for the size of E5. You just as a saving cost.
Very particular one about PowerPoint. Okay, show that it's well prepared.
Yeah. So we have this. We consulted the companies on the cost, and then we make some assumptions on the distance that can be covered by the E5 ship on the full charge. So the assumption is the ship will start from one port fully charged, go to the charging point, become empty, fully recharge from the charging point, and then go to the final destination. Okay. And when you reach the final destination, the battery is also fully drained. Okay, so this is A to B with one charging in between to carry cargo, and then the ship turns via the same route, right? Go back to the charging point empty, and then go back to where the cargo need to be reloaded. So we just estimated the ship will just repeat on the same route over and over again. Simple assumption, not realistic, but we would validate this further with some other data. And then we can calculate the number of trips this trip is able to make maximum, and how much cargo this trip, the vessel can carry. In addition, we then make assumptions on power generation technologies. So these are public numbers that's reported worldwide. It's not our data on the power generation technology. Also, the lithium-ion batteries. It's also taken from some studies. The details are actually in the Asian Development Bank working paper that we published in our preliminary analysis. So what happens is we look at what we call a net present value calculation. So what happens is in the economic calculation, we have the investment cost, you have the maintenance cost, fuel cost, decommissioning cost, and a bit of salvage value from the ship. You can calculate what is the total cost of ship, total cost over the lifetime of this vessel. And then with our assumptions, you can also calculate what is the total amount of cargo the ship can deliver based on our assumptions. Likewise, we can also compute what is the levelized cost of electricity generation from those offshore power sources. So the levelized cost of electricity from those offshore power sources would then be the fuel cost for the electric vessels. So in the end, we compute the dollar per ton of cargo delivered from point A to point B. So interestingly, we see that, well, based on the assumptions on the cost, offshore wind is kind of less competitive. It's primarily dependent on how much the cost is. If in the future the cost really drops to the level PV or maybe even lower, then of course it'll be more competitive. But as of now, as of the cost number we get, it seems to suggest that the floating nuclear power plant is economically competitive. So, and I also only want to emphasize it's just economic calculations. Okay, we didn't really consider, for example, safety, security, and all that things. So we just assume that it will be under normal operations, normal cost. Okay, and we did some further test, if you like, by imposing a carbon tax. So by looking, if you impose a carbon tax, so this assumption on the tax is based on the EU ETS carbon price, where we just assume that rather than taking the EU ETS approach, we just slap a carbon tax on the use of fossil fuel. And the BAU or business as usual scenario assume a $25 per ton of CO2 flat from 2020 to 2050. And then we also assume a high tax scenario in which the tax will increase from 25 to 150. Which is really a high end, but that's what most of our European counterparts are saying. That's actually a reasonable carbon tax in order for some of these clean technology to make sense. So we did another computation on the conventional fuel. So this figure on the right-hand side is solely produced for the conventional marine fuel vessels. But then the argument, you might say that, well, as compared to nuclear, it seems to be that electrification is already cost competitive. Why are we talking about tax? So of course, if you just look in theory, offshore charging seems to be competitive depending on the choice of technology, floating nuclear power plant. But there are other assumptions that we didn't fully address, or rather we have not fully accounted for, although there are some implicit assumptions. So for example, utilization rate of the charging station. Right now, we only have one ship, okay? So they come here, charge, go, and then only during charging, if you think about in a practical situation, only during charging, you actually use electricity. When the ship is not there, the electricity has to go somewhere, or not producing electricity, or just so-called curtailment, right? You don't use it. So the question is, with excess electricity, if you're just wasting it, then the levelized cost of electricity formula is flawed. You can't even use that formula. So how do we deal with electricity? So the implicit assumption is the offshore charging stations might not be as offshore as we think, in the middle of the ocean, like 1,000 kilometers away from shore. It's probably not going to be the case. Maybe 50 kilometers, maybe at most 100 kilometers. So there could still be a submarine power cable to channel electricity back on shore, where if you have an industrial setup, industrial facility setup, or you have cities, then these cities or industrial facilities can still benefit from the clean electricity from these offshore settings, so that no matter how much electricity the floating power stations are producing, they are fully utilized. So they are part of the economic calculation. And then you might argue, well, that's a different user paying for this, right? A ship is paying for something else, whereas the electricity going onshore is on a different cost, right? And people are paying a different price. But of course, in this case, you just assume that the LCOE is accounted for every user. And then another question we have not fully addressed in the study, but we believe that some insights can be derived, is that right now we're just assuming you're going from point A to point B with only one charge in between. What happens if you really want to test the case where we're going from Singapore to Qatar, and you might need, I don't know, 10, 20 chargers in between, right? How does that impact your shipping arrangement, your shipping schedule, for example? 15 minutes for one charge, well, okay, 15 minutes of the pit stop is not really a big deal. But if you have 20 of that gives you 300 minutes. And if you need more, it's even more time on the road, right? So how does that impact the overall economics of electrifying vessels or long-haul vessels? So that is something that's yet to be tested. So no matter how realistic we want the assumption to be, we don't really have a practical reference, on a marinized offshore charging station. We do not really know. I mean, we have some ideas, but we do not really know what are the real engineering challenge or implementation challenge there are. How easy or how difficult to install, commission, and maintain a marinized battery energy storage. If something goes wrong, what do we do about it? High power induction charging. Yes, there are discussions about high power charging plug-in for electric cars, maybe even buses. And you could have relatively high power induction coil embedded underground, underground. So there are buses passing by, you can do opportunistic or induction charging as the cars and buses passing the designated lanes. But in the context of offshore engineering, this is a whole new level of challenge. And then, of course, yes, the logistics of installation and maintenance. Deploying offshore wind, offshore PV, and today deploying floating nuclear power plant, we have experience. But to deploy an offshore or even floating charging station, there's still a lot of engineering questions to be addressed. What is the size and shape, and how does the ship approach a charging station? What is the charging arrangement? Is it fully autonomous? Then how do you manage that, right? I mean, so these are the engineering, maybe technology challenge. The other question is, so how do you price the charging? Do you have a meter for individual companies? No, do they have a meter on the ship? Is there a meter on the floating platform? How do you know which company, whose ship is coming and charge? And do you even want to consider time of day price or time of year price, depending on weather conditions or operating costs, etc. So there's a whole lot of questions that's not even answered. And really the final question, this is where I'm getting in, challenging my own levelized cost of energy, is who's actually going to pay for the upfront installation cost, and who is going to bear the risk? Is it just going to be, power companies says, we're just going to finance the project, we pay for everything, and you, shipping company, as a user, as you pass by, you use it and pay per use. If that is the model, then what is the payback for the power companies? And if you say, okay, maybe we do a joint financing, joint mechanism, and then the question is, so what is in it for each of the stakeholders in doing this, electrifying, placing offshore charging? And then, of course, in the context of floating nuclear power plant, but maybe not just the floating nuclear power plant, in general, the safety and security of this offshore charging station is one I believe will be very critical, right? Especially moving into the future when you're looking at systems becoming smarter, a heavy reliance on satellite link, if it's really offshore, or maybe the so-called the greater internet, where you are subject to hacking activities, so cyber terrorism. So then the question is, if there is a cyber attack on the offshore charging station, what could happen? And how do you defend your charging system? Then, of course, there is the the greater or more strategic considerations of the floating platform. This I have discussed with some of our participants and some of our experts. On the surface of the sea, you have ships, right? These are your so-called, I wouldn't call them low-hanging fruit customers, but these are the most obvious customers. But what about underwater? There are other vehicles, for example, underwater vehicle for scientific mission, surveying the marine life, surveying bottom of the ocean. These are probably powered by electric motors as well, having a battery. So can they be another customer using and accessing this infrastructure? And if that's the case, then what is the greater scheme of pricing or business model if you serve or cater to different customers and for different purposes? And this is from one of my friends. He's also listening to our webinar. This is a bridge or connection between Malmö and Copenhagen, so between Sweden and Denmark. So it's a real feat of engineering. I mean, they have the Transocean Bridge. After that is a tunnel, right? And the tunnel, if I'm not wrong, the tunnel allows both cars and light rail trains to pass through. So this is really it's a very convenient connection between Sweden and Denmark. So he was saying, if you call this person Hans Cavalli, I mean, if there's no water between Malmö and Copenhagen, there would have been a road already. So what does this say? If you do not have ocean and have vessels, then you would have cars building roads and have cars traveling. And if that's the case, and if you electrify road transport, then there's bound to be charging. So you have to have charging stations anyway. So it's like, if you want to make the convenience, you want to achieve certain goals, then something has to be in place. Right? And then you really need to think about, and engineering would really need to make this happen. So what do we need to do? Or rather, what is next? It is not, if you rely just on the shipping companies or individuals to think about what to do next, right, it will be very difficult. So a strong policy push will still be desirable, right, either at the international level or the national level, or maybe even at the multilateral level. Putting a stronger carbon tax or other environmental regulations, so you just cannot, putting a standard, you just cannot emit by so much by each year. And that would naturally give a clear signal of where the shipbuilding companies or the shipping industry would go. But then, of course, there are different layers of considerations beyond technology or even cost. And there's political considerations, there is industry development, different national priorities. Oops. And then, as you might agree, after going through this webinar, you would have agreed that if you want to fully electrify vessels, it is not just about what the individual can do. In fact, it involves the cooperation of multi-stakeholders, the shipbuilding companies, the operators. These are the ones that will need to be, if you like, leading the transformation, but also other economic sectors, manufacturing sectors, the so-called refinery or petroleum sectors, the energy sectors, even the different authorities in the government. They all have a role in driving electrification, if electrification is deemed to be the future of decarbonizing the shipping industry. And of course, to make things happen, you cannot just rely on just one agent or one player in the society. And I think the public and private sector really needs to collaborate and work more closely in terms of research, development, demonstration of relevant technologies. It's not just about offshore charging. Offshore charging is basically a basket of different engineering and technologies that needs to be developed and tested. So with the academic institutions or research centers taking the lead in technology innovation, I think the public and private sectors really need to work together in transferring or translating those technology, those know-how into something that's more practical, maybe even reducing the cost of floating offshore charging stations. So I really want, just at the end, I really want to mention, Singapore really putting in a lot of attention in maritime electrification. There is even a joint call between the MPA and Singapore Maritime Institute back in 2020 on electrification of hovercraft. So Singapore is not the only country. Other countries are in the region, and other countries around the world are also looking at electrification. So in the future, perhaps, several ports wants to electrify, or several companies want to take the lead, offshore charging station might not be that far away. So with that, I would like to conclude my presentation. Thank you very much for the kind attention.
Okay, thank you very much, Dr. Victor Nian, for the interesting presentations. So now we're going to the Q&A sessions. If you have any questions to Dr. Victor Nian, please post it in the chat group and we'll read out the questions. Right. So I see some question coming in.
Yes.
Let me see. All right, the first one from Emre is on the EGCS water from scrubbers. Okay, it's more restricted from a lot of ports worldwide. So in this context, exhaust gas cleaning is still a valid alternative.
I mean, this is actually a very interesting, a very important question. When people are talking about long-term pathways, it's also important to look at near-term solutions. So is cleaning up exhaust gas a valid alternative? I think the answer is probably yes. You still have to look at, what in the immediate term, how much you can decarbonize, and what really is the cost of retrofitting. We're not talking about new build, just we talk about existing ships. So if it can be demonstrated that it is cost justifiable, then I think it can be a possible alternative in the near term.
All right. So this scrubbers is still meant for older ship, as commented by Charles. And for most new ship, they go for alternative fuel like LNG.
Yes, it's most probably for existing ships. I think for new build ships, we already hear companies wanting to go for LNG and other alternative fuels. Bioenergy is also something that is being discussed, but energy intensity is a major concern with those fuels.
All right. Okay, we have one question from Peter. So some believe that the only viable technology which can deliver durable combinations of close to zero emissions, marine level reliability, walkaway safety, and competitive economics for long-distance ship is onboard small-scale nuclear reactor energy. So does it not remain the most obvious longer-term solution?
Yeah, this is actually a very interesting question. Well, personally, I believe nuclear energy can be a long-term solution. In fact, it is. I mean, there's a lot of other people are saying the same. It's not just myself. I mean, if you're really concerned about climate change, and if you really need to take urgent actions to mitigate the warming climate, then nuclear actually is a near-term solution rather than a long-term solution. So then the question is, can we put a nuclear reactor in the ship? The technical answer is yes. Right? Nuclear submarines, aircraft carriers, we already have nuclear reactors on board. So this is nothing new. Even for Russia, there is nuclear-powered icebreakers. So even for civilian use, we see nuclear reactors. Is it possible to put nuclear reactors on board a ship? Yes, it is possible. And it's probably not a technical problem. However, it could be very much a political or security problem. If you think about a nuclear vessel moving along the streets of Malacca, what happened during COVID-19 is there's a surge in piracy in our neighborhood. Right? So if you have a nuclear powered vessel and somehow you get hijacked by pirates, hopefully not, then the consequences can be tremendous. So it is not so much of an economic and technical challenge, I believe, but in the long term, there has to be a greater cooperation in maritime safety and security if we want to enable nuclear powered civilian ships.
All right. So following these questions, how about what are the policies required for the mainstream uptake to implement nuclear reactors into ship?
I think the most critical thing is, first of all, the public really has to accept the fact that nuclear reactor can be safely placed in the ship. So getting over with the public perception or acceptance may be a major challenge, but this is not impossible. But I still think that maritime security will remain an issue if we want to have civilian-powered nuclear vessels. I had some debate with my contacts, even in Shanghai Maritime University and other places. We were thinking, well, if nuclear really is a critical asset, and in fact it is a critical asset by many countries' definition, why can't we make better defense, self-defense for the crews, right? I mean, if you really have piracy, can we give exceptions of the crews of the vessel? I mean, I don't want to use the word to arm them, but lack of better choice of word, give them reasonable arms. But then it creates a counter problem. I mean, if you arm the crews, and then when the ships, let's not talk about any other country, let's say the ships dock in Singapore, want to do refueling or maintenance. Not refueling, I mean, do maintenance. You have a team of crews, armed crews, coming to our seaport. I think that would probably create a lot of, raise eyebrows to our civil defense and also, the citizens of Singapore. So that actually is that kind of issues rather than a technical or economic question. So really, it needs a coordination of different ports, right? And also, how do we safeguard these vessels en route to ensure that there's minimum impact from piracy, or maybe even no implications for piracy, and then that I think will be the enabler for
All right.
nuclear reactors on ships.
Okay. Right. Thank you. So Julia has one question also on the nuclear floating power plant. So the one that you are presenting, is it based on the pressurized water reactors?
Yes. The active aluminum salt is a typical, or rather I would call it mature PWR technology. It is not based on molten salt.
All right. So have you considered molten salt reactor, which Julia believe that it will further enhance the competitiveness?
Mm-hmm. Yeah. So actually, this is an area where I'm very actively seeking out collaborators. Right? So for the purpose of the study, if you recall the slides that I used for the assumptions, there's already a tremendous amount of assumptions in the study. So we really want to base on something that is as trustworthy as possible. So PWR being the mature technology and being something that is already deployed, we use that as a reference. But we will be very much happy to consider molten salt reactors if there are experts who are able to share with us some insights and data, even implementations. We'll be very happy to expand the scope of our study to cover molten salt or even other type of reactors.
All right, thank you. All right, one question from Sis Harry. So this is on the hovercraft. Okay, hovercraft are short hulls and hence are better candidates for electrification. So not without concerns on the total cost of ownership. As Peter has pointed out, these onboard reactors or even ammonia may threaten undertaking fluid-borne research into long-haul electrifications. And hence wondering if there are any enough expression of interest in commercializing this idea.
That is actually a very good question. We do like to see a stronger effort in electrifying the maritime sector. Offshore in the open ocean, there's tremendous energy potential. You have nuclear energy, wind energy, PV energy. And maybe even in the future, there can be new innovation in technology, maybe even ocean energy. So electrifying maritime transport actually makes sense in the long term. But there will definitely be competitions from ammonia, even LNG. So then, of course, taking one step back, there may be competitions from the perspective of maritime fuel. There might be something that's counterintuitive if you consider the life cycle of fuel production. Ammonia, LNG, maybe you can argue this is coming from naturally evolving source. But ammonia is actually a fuel that needs to be manufactured. And the ammonia manufacturing process is quite energy intensive. Likewise with methanol production. These are all quite energy intensive processes. And LNG is also not without energy penalty. So then the question is, if you consider the entire life cycle of these different alternative marine fuel, does ammonia, methanol, or even, I wouldn't want to say LNG, this manufactured fuel, do they make sense? How clean are they compared to manufacturing the bunker fuel? So yes, there will be competition, but there will always be then there might also be perception and other issues around it. But I guess, this is what I think can be done, as a public-private sector collaboration. Something has to be done. Right? Somebody has to make the first step in demonstrating that the technology actually works, right? And then demonstrating that there is a possibility from an economic point of view, it actually makes sense. From there, I think the future path of competition or maritime fuel will become clearer.
All right. So all these alternative fuel, are they ready for mass productions to be commercially viable?
I believe for ammonia, the process is pretty mature.
All right.
We are quite familiar with ammonia. LNG, yes, we're familiar with LNG. Methanol, yes, we have very mature technology to produce methanol. But then the problem with ammonia is ammonia is combustible, but it's not as combustible as the other fuels. So you very often need a pilot fuel to actually burn the ammonia. And the pilot fuel happens to be diesel. So whether it's clean enough to use ammonia is actually a consideration. And then ammonia doesn't really have the energy density as compared to IFO. So if you are relying on existing vessel design, same tank volume, you replace with IFO with ammonia or with bioenergy, you're going to sacrifice on mileage of the voyage mileage. That is for sure. Whereas with batteries, I think there is a possibility to actually extending the range by a significant amount. How much, I'm not very sure because I'm not a battery expert, but I do hear, or rather saw news that the solid state batteries or lithium polymer batteries can really extend the range of electric vessels on a full charge, and the energy density will be many times higher. And of course, there is this discussion about graphene technology being used in battery systems, so it will really improve the efficiency or energy density of batteries. So in the future, maybe electrification can be an option together with floating charging stations, for example, nuclear or offshore wind.
All right, thank you. Okay, so here we have a few questions also related to the molten salt. So Peter says that it's still probably still at least 15 to 20 years away in terms of commercialization. And then do you see MSR as a threat or opportunity towards Singapore's status?
Yes. Well, you see, sometimes I think the issue with new technologies, I wouldn't really exactly call it new technologies. With new technologies, people tend to have, or rather many industry likes to have the wait and see angle. I can fully understand why this is the case because it's survival. I mean, it's business. It has to make sense for anybody to devote money into it. So then the question is, as Peter was saying, if molten salt reactor is 15 to 20 years away before commercialization, if you do a calculation, today is 2021, sorry, it's 2021. We passed by 2020 already. 15 years away would mean 2035, right? It's well beyond 2035. And we actually, if you look back at the IPCC or the IEA, we do have targets for 2030, right? The long term is 2050. So the question is, do the whole industry sit tight and wait for just nuclear reactor technology to become available before we take action? Or should other industries, like battery industries, induction charging producers, all look at their technology together? Maybe by 15 years, there will be amazing technologies that can really fulfill that kind of charging power. I mean, right now we're looking at, I think, 15 megawatt for our ship. I didn't really show the results, but I think the charging power is about 15 megawatt for you to have to charge the ship within 15 minutes. If you're thinking about a VLCC vessel, 15 minutes charging, that will be a tremendous amount, maybe in the range of 100, 200 megawatt. If you just wait, that technology will not come safely. Not saying impossible. I mean, you can just boost out the current or the power rating you can charge, but how safe it is and how much damage it would induce on the batteries. So I think the co-development or co-innovation has to exist. Maybe sorry, it's not the word. Co-innovation is not the right word. It's co-development has to happen today while waiting for nuclear reactors to become available. If not, it becomes a shame. You have the nuclear reactors ready to be deployed, but you cannot charge. You don't really have the electrification part, and that was supposed to be a low-hanging fruit as compared to nuclear reactors.
All right. So for the E5 vessels, the Japanese vessels, how fast is the fast charging and what's the capacity?
Unfortunately, I did not manage to find the charging power for the vessel. So we just made an assumption of it. And in fact, okay, rather let's look at it this way. The numbers we got are based on assumptions, right? And we think that going from point A to point B over 300 kilometers, 15 minutes charging time is probably the maximum the company is willing to tolerate. So if you charge in 15 minutes, you need to go for like 50 megawatt of charging power. Right? So this is actually a reverse way of thinking. Rather than assuming, knowing what its charging power is like, if they had to charge, then this is probably the charging power requirement for the ship. And likewise, the bigger the ship goes, the higher the charging power will be needed. So I think, this is just our imagination. We think that if you want to enable electrification, the charging power and the size of the battery has to go hand in hand. So you really have to allow really high charging power to become available before you can electrify ships.
All right. So in your research, do you consider hybrid vessel, taking fossil fuels and electric together?
I believe this is an area of interest. In our discussions with shipping companies, there are companies mentioning that they're considering this hybrid electric and LFO, and also dual fuel ships. So you can actually switch between the traditional bunker fuel and LNG, if I'm not wrong. So you can have different fuel options. So, but we didn't consider that in our present study, but that will be very much be our interest, as we build up these so-called technology pathways for future.
Okay, all right, thank you. So Julia has a question also on the battery-powered vessel. So is the cost competitiveness between the battery-powered vessels and other alternatives being considered? So other alternatives like green electro fuel vessels, nuclear vessels, fossil fuel vessels.
Well, we did consider the other vessels, but we have not come up with the results yet. And actually, we are also looking for possible collaborators to give us more guidance and data on the alternative fuel productions, because I think we need to know the cost of fuel, and we also need to know the other technical parameters, for example, capacity, refueling, maintenance, how does that influence the maintenance cost. But yeah, that's an area we are very interested in, but we have not done the actual calculations yet.
Okay, all right, thank you. Okay, Jianying has a questions on the transition to recap. Hybrid ships will make up a significant portion of the fleet. So in your study, did you consider how the offshore charging station can serve the hybrid ships?
I think if I understand the context of the question, I believe this is something along the lines of like hybrid vehicles, right? You have plug-in hybrid vehicles. So you have a relatively larger battery, you can plug into the grid and charge, and at the same time you have some fuel on the side. So I think the answer is yes, you can actually derive some insights from our study on the hybrid arrangement. It's a matter of two fuels, right? And these two fuels actually don't interfere. So actually, if the two fuels interfere with one another, that is actually going to give some complications, like the non-plug-in vehicles, right? So you can charge the batteries as you use an internal combustion engine like the Toyota Prius, or you can do just standalone. So if you do a standalone, like what we do is you basically consider that E5, you have batteries at the bottom, right? We think it's at the bottom, maybe it's somewhere else. And then you have electric motor engines. On top of that, you have the normal conventional combustion IFO engine on the side. So depending on the powertrain design, if they are totally independent, I believe it's almost like modeling two ships, in a sense, two ships on the same vessel. And then you can separately account for the cost and efficiency from our study. You just have to fractional attribute the different cost components to the different part of powertrain. Whereas I think this problem will be more interesting if the vessel is allowed, or rather the combustion engine is allowed to charge the batteries. That will make the question actually more complicated.
All right, thank you. So we do not have any more questions from the chat group. So probably I end with one question. So in terms of COVID-19 pandemics, how does it affect the fuel consumptions or demand supply in Asia or in Singapore?
That's actually a very, very important question. So as during just the beginning of COVID-19, there is this global lockdown, not just the international passenger or tourism. The international shipment and transshipment also suffered a lot. I mean, basically trade went down by a significant proportion. So of course, international shipping suffer from that, or in a way benefit from that because it's natural decarbonization in the sense. But then of course, nobody wants to see this. It's a shipping that is the economic development, is a lifeline of the economy, and is a lifeline of trade. So they actually impact Singapore quite a bit. I mean, if you look at the economic data you get from statistics department in Singapore, yes, we do get serious impact by the the going down trend of international shipping. But now, with the reopening of borders and reopening of trade, we're actually seeing the other negative impact. So because the downward trend in trade, a lot of companies are projecting, trade is going down. We don't really need to add a new fleet. We don't need to make new investment because ships are really costly. And you don't have the volume, there's no payback. So why don't we do that? As that happens, actually after COVID-19, it's actually just recent few months, you actually see a resurgence of the shipping demand across the world. And some of the companies I talked to, actually now they're having trouble bringing in goods or manufactured products from China and from other parts of the world because it's just not enough shipment, not enough shipping services provided by by the major companies. So I think really is a twin blade sword in how this the COVID-19 impact shipping. On one hand, it reduces the demand, creating an impression that this will go down. And it also the cost becomes lower, right? I mean, rather cost of shipping becomes lower. Mm-hmm. As the sudden surge, the cost of shipping will go up. And then what will happen is a lot of companies will see an opportunity in this upward trend to make investment. And at some point in time, if you think in terms of the system dynamics, right, people are making a lot of investment, 5-6 years down the road, you see a huge amount of ships entering the fleet. And by the time, the question is, do we really that huge amount of demand in 5 or 6 years, 5 years or 6 years time, based on today's trajectory of economic recovery? And if it's not, what is going to happen to the shipping prices? Is it going to crash down again and then come back? So I think there is this issue about stability post COVID-19, rather in addition to just sustainability issues. So yeah, it will be something interesting to study, I guess.
All right. Okay. All right. Thank you, Victor, for answering the questions. So I guess there's no more questions for Victor, and I would like to thank Victor once again for giving this presentation. Thank you.
Thank you, Dr. Tay.
Yeah.
Thank you very much.
I would